Bismillahirrahmanirrahim. In this lecture, we study about the linear differential equation of higher order with variable coefficients. We can solve this type of differential equation by two methods. First, Cauchy linear equation, and second, Legendre's linear equation. So first we are going to discuss about the Cauchy linear equation. Cauchy linear equation, it is of the form x to the power n dn y over dxn plus a1 x to the power n minus 1 dn minus 1 y over dxn minus 1 plus up to an y is equal to x, where a1, a2, an are constants and capital X is a function of small x. This can be reduced to linear differential equation with constant coefficients by substituting x is equal to e to the power t or log x is equal to t. Then dy by dx is equal to dy by dat into dt over dx, which is equal to 1 by x dy by dt, or x dy by dx is equal to dy by dt, and d2 y over dx2 is equal to d over dx dy by dx is equal to d over dx 1 by x dy by dt, which is equal to minus 1 by x square dy by dt plus 1 by x d over dx dy by dt, which is equal to minus 1 by x square dy by dt plus 1 by x d over dt dy by dt into dt over dx, which is equal to minus 1 by x square dy by dt plus 1 by x square d2y by d2 dt square, implies x square d2y over dx2 is equal to d2y over dt square minus dy by dt, which is equal to d minus 1 y. Similarly, we can write x cube d3y over dx cube is equal to d minus 1 d minus 2 into y, and so on. This way the substitution reduced the given homogeneous equation to linear equation with constant coefficients. Now the second method was homogeneous linear equation. It is of the form ax plus b to the power n dn y over dxn plus a1 ax plus b to the power n minus 1 dn minus 1 y dx to the power n minus 1 plus an y is equal to capital X. Equation number 1, where a1, a2, an are constants and capital X is a function of small x. After putting ax plus b is equal to e to the power z, we get the linear differential equation with constant coefficients, and we know how can we solve differential equation with constant coefficients. Now we are going to solve the examples. Example first, solve d2y over dx2 plus 1 by x dy by dx is equal to 12 log x over x square. Solution: the equation can be written as x square d2y over dx2 plus x dy by dx is equal to 12 log x, which is of the form of Cauchy's linear equation, so that putting x is equal to e to the power t, we get d minus 1 y plus dy is equal to 12t After solving this equation, d2y over is equal to 12t implies y is equal to 2t cube plus c1 t plus c2. This y is coming after integrating this equation two times. Therefore, solution y is equal to 2 log x cube plus c1 log x plus c2 because t is equal to log of x. Now second example, solve x square d2y over dx2 plus x dy by dx minus y is equal to x cube. The given equation is in the Cauchy's form. Putting x is equal to e to the power t, we get d minus 1 plus d minus 1. Y is equal to e to the power 3t implies d square minus 1 y is equal to e to the power t, which is the linear differential equation with constant coefficients. We get complementary function is equal to c1 e to the power minus t plus c2 e to the power t is equal to c1 over x plus c2 x because e to the power t is equal to x, and particular integral is equal to 1 by d square minus 1 e to the power 3t. So putting d is equal to 3, we get 1 by 9 minus 1 e to the power 3t, which is equal to 1 by 8 e to the power 3t, which is equal to 1 by 8 x cube because e to the power t is equal to x. So the complete solution is y is equal to complementary function plus particular integral. This is equal to c1 over x plus c2 x plus 1 by 8 x cube. Example third, solve 2x plus 3 whole square d2y over dx2 minus 2x plus 3 dy by dx minus 12y is equal to 6x plus 9. The given equation is of Legendre's form. Then by putting 2x plus 3 is equal to e to the power t, we get 2 square dd minus 1 minus 2d minus 12 into y is equal to 3 e to the power t, where d is equal to d over dt, or 2d square minus 3d minus 6y is equal to 3 by 2 e to the power t. Auxiliary equation is 2m square minus m minus 6 is equal to 0, whose roots are k1 and k2, where k1 is equal to 3 plus a root 57 over 4 and k2 is equal to 3 minus root 57 over 4. Therefore, the complementary function is equal to c1 e to the power k1t plus c2 e to the power k2t. We can write again this is equal to c1 e to the power t to the power k1 plus c2 e to the power t plus k e to the power k2, where e to the power t is equal to 2x plus 3. So we will put here e to the power t is equal to 2x plus 3. We get c1 2x plus 3 whole k1 plus c2 2x plus 3 whole k2. Now we need to find the particular integral, which is equal to 1 by 2 d square minus 3d minus 6 into 3 by 2 e to the power t is equal to 3 by 2, because 3 by 2 is constant, so it will come outside, and putting d is equal to 1, we get 1 by 2 minus 3 minus 6 e to the power t, which is equal to minus 3 by 14 e to the power t, equal to minus 3 by 14 2x plus 3. Complete solution is y is equal to complementary function plus particular integral, which is equal to c1 2x plus 3 to the power c1 plus c2 2x plus 3 to the power k2 minus 3 by 14 2x plus 3, which is the required solution of the given differential equation. Now we are going to solve linear system of ordinary differential equation. We will understand the method of solving the linear differential system of ordinary differential equation by the following examples. First, question example 1. Solve the simultaneous equation dx over dt minus omega square y is equal to cosine of at, and dy by dt plus omega square x is equal to sine at. The solution, the solution, the given equation can be written as d minus omega square y is equal to cosine of at, equation number 1, dy plus omega square x is equal to sine of at, equation number 2. Differentiating equation 1 with respect to t and multiplying by omega square in equation 2 and adding them, we get what we get: d square x minus omega square dy plus dy omega square plus omega to the power 4 x is equal to minus of a sine ax plus omega square sine ax at, implies d square plus omega to the 4x is equal to omega square minus a sine at, question number 3, which is the linear differential equation of second order with constant coefficients. The roots of auxiliary equation m square plus omega to the 4 is equal to 0 are m is equal to plus minus I omega square. Therefore, complementary function is equal to c1 cosine omega square t plus c2 sine omega square t for particular integral omega square minus a is into 1 by d square plus omega to the 4 sine at. This is equal to omega square minus a divided by minus of a square plus omega to the power 4 sine at is equal to 1 by omega square plus a sine at. Complete solution for x is equal to c1 cosine omega square t plus c2 sine omega square t plus 1 by omega square plus a sine at. Substituting the value of x in 1, we get minus of c1 omega square sine omega square t plus c2 omega square cosine omega square t plus a over omega square plus a cosine of at minus omega square y is equal to cos at, implies y is equal to minus of c1 sine omega square t plus c2 cosine square t minus 1 by omega square plus a cosine of at. Question number 5. Equation 4 and 5 together represents the complete solution of the given equation. Now the next problem. Solve the simultaneous equation dx over dt plus x is equal to y plus e to the power t, dy over dt plus y is equal to x plus e to the power t. Solution. The given equation can be written as d plus 1 x minus y is equal to e to the power t, d plus 1 y minus x is equal to e to the power t, equation number 2. Multiplying by d plus 1 in equation 1 and add in equation 2, we get d plus 1 whole square x minus d y minus y is equal to e to the power t plus e to the power t. D plus 1 y minus x is equal to the power t. Subtracting this, we get d plus 1 whole square x minus x is equal to 3 to the power t, implies d square x plus 2 dx plus x minus x is equal to 3 e to the power t. So x will be cancelled and we get d square plus 2dx is equal to 3 e to the power t. Equation number 3. The roots of auxiliary equation m square plus 2m is equal to 0 are m is equal to 0, m minus of 2. Complementary function is equal to c1 plus c2 e to the power minus 2t, and particular integral is equal to 1 by d square plus 2d 3 e to the power t. This is equal to 3 by 1 plus 2 e to the power t is equal to e to the power t. And therefore x is equal to c1 plus c2 e to the power minus 2t plus e to the power t. Equation number 4. Substituting x in equation 1, we get 0 plus e to the power t minus 2c2 e to the power minus of 2t plus c1 plus c2 e to the power minus of 2t plus e to the power t minus y is equal to e to the power t, implies y is equal to c1 minus c2 e to the power minus 2t plus c e to the power t. Equation number 5. Equation 4 and 5 together represents the complete solution of the given equation. Now we are going to study about the series solution of a of a linear ordinary differential equation of second order with polynomial coefficients. The method of finding power series solution is generally applied to second order or differential equation of the type px d2y by dx2 plus qx dy by dx plus rx into y is equal to 0. Equation number 1. Dividing by px in equation 1, we get d2y over dx2 plus px small px into dy by dx plus small qx into y is equal to 0, where px is equal to capital Qx over capital Px and Qx is equal to capital Rx over capital Px. Before we develop the method of solving the equation 1 by the infinite convergent series y is equal to summation 0 to infinity arx to the power m plus r, it is necessary to find whether this method is applicable to all second order differential equation of type 2. First, regular functions. A function fx is said to be regular at x is equal to a if it possesses derivatives of all orders in some neighborhood of a. We know that if a function is differentiable any number of times in some neighborhood of a point x is equal to a, it can always be expressed as a power series of the form summation r is equal to 0 to infinity ar x minus a to the power r. Thus, in other words, a function fx is called regular at x is equal to a if it can be expressed as a power series of the form summation r is equal to 0 to infinity ar x minus a to the power r. Second one, ordinary point. The point x is equal to a is said to be ordinary point of the differential equation 1 if both px and qx are regular functions at x is equal to a. Thus, x is equal to a 0 is an ordinary point of the differential equation 1 if both px and qx are expressible as power series of the form 0 to infinity arx to the power r. Now third one, singular points. A point which is not an ordinary point or a differential equation of a differential equation is called a regular singular point of that differential equation. For example, consider the differential equation 1 plus x square d2y by dx2 plus 2x dy by dx minus x square y is equal to 0. Here px is equal to 2x over 1 plus x square and qx is equal to minus of x square over 1 plus x square. It is easy to verify that px is equal to 2x 1 minus x square minus x to 6 plus up to qx is equal to minus of x square 1 minus x square plus x to the power 4 minus x to the power 6 plus up to, and therefore x is equal to 0 is an ordinary point of 3. Next consider x square d2y by dx2 plus 2x dy by dx minus 1 plus x square y is equal to 0 equation number 4. Here px is equal to 2 by x, qx is equal to minus 1 plus 1 by x square. Clearly px and qx are not regular function, therefore x is equal to 0 is not an ordinary point of the differential equation. Actually x is equal to 0 is singular point of the differential equation 4. Regular singular point in the differential equation d2y over dx2 plus px dy by dx plus qx into y is equal to 0 if px and qx are not regular at x is equal to a, but x minus a px and x minus a square qx are regular there, then x is equal to a is called a regular singularity of equation 2. Irregular singularity. Lastly, if px qx x px x square qx are not regular at x is equal to 0, then the point x is equal to 0 is called regular singularity of differential equation 2. In this case, the differential equation has no series solution.